In this lesson, we will discuss U-tube manometers. The limitations of a piezometer tube manometer can be overcome by using a U-tube manometer, which is a manometer that consists of a tube that's shaped like the letter U. In the image on the right, the cross-section of a pipe is shown and a U-tube manometer has been attached to the right side of the pipe. A second fluid, called a gauge fluid, is placed inside the tube and it has a higher specific weight than the fluid in the pipe. The use of a gauge fluid means that the pipe could be filled with a liquid or a gas. Additionally, the U shape of the tube means that the pressure in the pipe could be less than the ambient pressure. And the pressure in the pipe can be much larger than the ambient pressure if the gauge fluid is relatively dense, like mercury. To get a sense of how the U-tube manometer reacts to changes in pressure, imagine the pressure in the pipe increases or the ambient pressure decreases. In that case, the gauge pressure would shift to the right. If the pressure in the pipe decreases or the ambient pressure increases, the gauge pressure would shift to the left. The amount of shifting that occurs depends on the magnitude of the change of pressure and the specific weight of the gauge fluid. We can determine the pressure in the pipe at point A by using the concepts from hydrostatics. Let's label a few important points in the manometer. Point B is at the same elevation as point A. Point C is at the interface between the fluid from the pipe and the gauge fluid. Point D is at the same elevation as point C inside the gauge fluid, and point E is at the interface between the gauge fluid and the atmosphere. The vertical distance between points A and C is h1, and the vertical distance between points D and E is h2. The pressure at point A is equal to the pressure at point B because those 2 points are at the same elevation in a continuous fluid. Now we need the pressure at point B. The pressure at point B is less than the pressure at point C by the amount gamma 1 times h1. So now we need the pressure at point C. The pressure at point C is equal to the pressure at point D because those 2 points are at the same elevation in a continuous fluid. Both points are in contact with the gauge fluid. The pressure at point D is equal to the pressure at point E, which is the ambient pressure, plus gamma 2 times h2. We have 4 equations and 4 unknown pressures. The pressure at points A, B, C, and D. We can solve these equations to find the absolute pressure at point A, which is the ambient pressure plus gamma 2 h2 minus gamma 1 h1. For the gauge pressure, we would subtract the ambient pressure. Instead of solving a set of equations, we can use a shortcut to find the pressure at point A. We start at the far end of the manometer and work our way toward point A. As we travel along the manometer, we follow 3 rules. We will add a factor of gamma times h when moving downward through a continuous fluid. We will subtract a factor of gamma h when moving upward through a continuous fluid. And we can jump horizontally between adjacent sections of the tube if the fluid is continuous between the 2 points. So let's start at point E, where the pressure is the ambient pressure. As we travel downward from point E to point D, we add gamma 2 h2. Then we jump across horizontally from point D to point C, which is allowed since both points are in contact with the gauge fluid. And as we jump from point D to point C, the pressure does not change because they are at the same elevation. Next we travel upward from point C to point B, so we must subtract gamma 1 times h1. And finally, there is no pressure change as we move horizontally from point B to point A. Now that we have reached our destination, we can set the entire left side equal to the pressure at point A, and notice that we obtain the same equation as when we solved the set of 4 equations above. The U-tube manometer also can be attached to another device instead of being exposed to the ambient environment. And here we connect the end of the tube to another device, perhaps a different pipe or a different section of the same pipe. Point E now corresponds to the interface between the gauge fluid and the fluid in the pipe, which has a specific weight of gamma 3. For this particular setup, the specific weight of the gauge fluid, gamma 2, needs to be greater than gamma 1 and gamma 3. Point G corresponds to the point in the center of the pipe, and point F is at the same elevation as point G. The vertical distance between points E and F is h3. Let's use the shortcut method to find the pressure difference between the pipe on the left and the pipe on the right. We start at point G, where the pressure is Pg. We move horizontally to point F, and there is no change in pressure. As we descend to point E, the pressure increases by gamma 3 H3. As we further descend to point D, the pressure increases by gamma 2 H2. Now we jump across to point C with no change in pressure. This jump is allowed because both points C and D are in contact with the gauge fluid. As we move upwards to point B, the pressure decreases by gamma 1 H1. And finally, we move horizontally from point B to point A with no change in pressure. We've arrived at our destination and set the left side of the equation equal to the pressure at point A. Usually it will be easy to look up the specific weights gamma 1, gamma 2, and gamma 3 in a fluids textbook or elsewhere, and it would be easy to measure the heights h1, h2, and h3. If that is indeed the case, we have one equation but two unknowns, the pressure at point A and the pressure at point G. So while we cannot determine the pressure in both devices, by rearranging the equation, we can determine the pressure difference between the two devices. That is, we can determine PA minus PG. And fortunately, in fluid mechanics, often only pressure differences are important.